All right, so the main objective for today is to kind of go and take another pass to the gradient boosting. I think it might have been, might appreciate another pass through. And anyway, we'll have some kind of extensions to talk about. And then we'll end a little early. I'll give back the tests, which will be adjusted or curved or something to make the grades better. Cool. All right, so let's stare at this. This is the gradient boosting algorithm from top to bottom. Let's walk through it a little bit. I guess I don't have to tell you guys to stop me with questions. So we initialize a function to all zeros, and then we proceed in stages. Each time we add a function from our base hypothesis space, and we maybe have a step, that's like a step direction in function space, and then we multiply it by a step size. All right, so the main first step is this thing that suddenly looks a little bit more complicated than we looked at last time, but it's the same thing. Let's just study it a bit. So this is going to be it's a vector of partial derivatives. We're taking a partial derivative with respect to the prediction of the function f on the training example xi. So pick a training example xi, all right? And then our function is going to make a particular prediction for xi. We would usually call that like yi hat or something, right? The prediction corresponding to xi. And what we want to do is we want to see how we would directly adjust that prediction for that input to decrease the loss. So if you want to see locally how you adjust a prediction to optimally decrease a loss, you take a derivative. So we're taking a partial derivative with respect to the prediction on the ith example. That's what this partial derivative is. Is that clear? OK. And what are we taking the partial derivative of? The loss, the sum of the loss on all the data. Now, of course, what's going to happen when we take this partial derivative of the sum? It's a sum of n terms. Which of them are relevant to this particular partial derivative? Only one of them, right? The only one of these summands in the sum that's relevant to the partial derivative with respect to f of xi is the one involving the ith example. So it's just the derivative of the loss function with respect to f of xi, which is the second argument. OK. So that's a partial derivative with respect to one example. We stack them up into, OK, there's one other thing. When you take a derivative at a particular location, right? We have a function, we're in a location, and we want to know what's the gradient or the derivative at that location, right? So it's not just enough to say, oh, we're taking a partial derivative. I need to tell you where we're evaluating the partial derivative. And where we're evaluating it is where we are in our iterative optimization, which is f sub n minus 1. So at the end of each step, at the end of the mth step, we have a prediction function f sub m. So here at the end of the m minus first step, we have this prediction function f sub m minus 1. Its prediction on xi is f sub m minus 1 xi. So that's where we're evaluating the derivative, right? Here's our prediction right now based on f sub m minus 1 for the input xi. I want to know how to adjust that position to best decrease the loss. So that's where I take the partial, all right? So it's the partial with respect to that evaluated at the prediction from the m minus first regression function. Is that clear back there? Questions? Bless you. OK. All right. We stack up the partials into a vector. That's the gradient with respect to the vector of predictions on all the input examples, training examples. And we call that g sub m, the gradient at the mth step. All right, so if we were doing kind of an unconstrained optimization, our gradient, our step direction would be negative g sub m. OK. So g sub m is just a vector. We're really optimizing, we're adjusting a function. So we're at f sub m minus 1, and we want to take a step to improve the function. We need to add a function to it. Okay, where does this function have to live in this setup? What function space do we want this new function we're adding to f sub m minus 1 to be in? Yeah, it has to be in the base hypothesis space. So how can we find a function in the base hypothesis space that's at least as close as possible to the unconstrained negative gradient step direction that we want? Yeah, we could, right, it's kind of like a projection. We want to find, here's the step. We want to find the function h in the hypothesis space, the base hypothesis space f, that's as close an approximation to this gradient vector as we can find. And that's the direction that we'll actually step in. And the minimizer, being in a function space, it's a function. It's something that we can add to f sub m. And when we add some multiple of h sub m to f sub m minus 1, we're still in the span of the base hypothesis space. This is a good, that's a direction that we can use. All right, and then the last piece is the step size. Typical would be you just have a fixed step size. 0.1 is actually a typical multiplier you often find. Theoretically, you can do a line search where you find the best step size. Yes, please.
Do you have any way to ensure that the h sub m is unique? The function that this approach.
OK, great question. So the question is, here we have a minimization over the function space of this objective function. Is there anything we can say to be sure that's unique? What do you think? What's convex? The function? OK, so the objective function is convex. OK, so all right, big picture, never mind this thing. To have a unique minimizer, we need strictly convex, a strictly convex optimization problem. So it has to have a strictly convex objective over, of course, a convex domain. So to have a convex domain, f would have to be convex, the space of functions. And then we would need this objective to be strictly convex. So that could guarantee it. But we have no constraints like that. This algorithm is agnostic to whether or not there's a unique minimizer. It's interesting. I don't see that that's a concern. Did you have something in mind why that would be a concern? OK. All right. Any more questions on this algorithm? It's a good time to ask. I have a couple of pictures. Yes? GM is a vector. GM is a vector. How big is the vector? The vector is as large as there are training points. Each entry of GM is a partial derivative on the prediction for the ith example. We want to see how to adjust the ith prediction to optimally decrease the loss. OK. All right, this may help you. This is what we're looking at here is a surface plot of R of f is the risk. It's the sum of the loss, the training loss, right? And we have the domain are these two axes, f of x1 and f of x2. So we have a prediction function, but we're only looking at its predictions on two training points, x1 and x2. Suppose the training set is of size 2. And as we adjust the predictions we make on each of those inputs, x1 and x2, so that's different points in this plane here, we have different associated risks, and that's the surface that we see. So we start at some function over in this corner whose predictions on x1 and x2, I don't know, suppose this is a unit square, it might be 1, 1, and the risk is quite high. And then we treat this as a two-dimensional optimization problem initially, where we just need to find the gradient in this space that gives us the steepest, well, gradient steepest increase, the negative gradient is the steepest decrease direction. So we'd want to go in this direction, and then this, and then this. But of course, taking these steps are not necessarily compatible with staying in our hypothesis space, the increments of the base hypothesis space. So what we have instead are, this would be the first gradient step, and we project it, whoops, we are off screen. We project it to the base hypothesis space. So this would be the step that we actually take, which would be the closest in the hypothesis space to this unconstrained gradient vector. Okay. Great. All right, so kind of a recap of what you need and what you get with gradient boosting. We have a loss function that we need to be able to take some kind of derivative, or at least subgradient of. We get to choose a base hypothesis space for regression, and we needed also an algorithm to actually solve the regression problem with that hypothesis space for square loss. And we're going to have a stopping criteria. How many steps of boosting do we take? And we need a step size methodology. And that's about it. So if you have all these inputs, you are ready to go. It's kind of plug and play for this algorithm. And this is pretty much, we're at state of the art. Well, we're at, let me not just say state of the art. Let me say what people actually use in practice if you want an effective, nonlinear regression or classifier. Gradient boosting is certainly high on many practitioners' lists. So this is a very good one to know about. Random forest also. And what's nice is they can be, well, gradient boosting can be adapted to any loss function, as we said. In practice, as far as hypothesis spaces, I think the vast majority of use cases are trees, regression trees as a base hypothesis space. We'll say a little bit more about those trees in a minute. Okay. All right, so trees are the primary use case. What kind of trees? Are they deep trees? Are they shallow trees? They're on the shallow side. So hypothesis space of regression trees of size j, where j is the number of terminal nodes. That's one way to measure the complexity of a tree, the number of terminal nodes. What would be another way to measure complexity of a tree? Of a binary tree? Yes, the height, the depth, right. The number of leaves is this. Terminal nodes are leaves, yeah. Okay, so different, if you have a gradient tree boosting algorithm, one of the parameters might be how many leaf nodes do you want to have in your trees of your base hypothesis space? Or it may say, what's the maximum depth you want to allow for your trees in the base hypothesis space? These are tuning parameters for a tree boosting algorithm. So decision stumps are used. So what's the form, think about it yourselves for a second. What's the form of the final prediction function if we use decision stumps as our base hypothesis space? So any kind of gradient boosting is going to be a linear combination of our base hypothesis functions. So we'll have, a sum of alpha. Let me not write that way. So the first one might be alpha I. Suppose our features are, suppose we have d features, x1 through xd. So what would a decision tree, a decision stump regression function look like? So it's going to be, you could write it as an indicator of, you get one splitting variable in a decision stump. So x3, for instance, less than or equal to 2.5. There. So alpha 1. So this would be one step of gradient boosting with a decision tree, decision stump. All right. Let's add another one. So let's make an actual number. Okay, f sub 1 is this. f sub 2 is equal to f sub 1 plus 2.1. Say again? Plus 6.8 x sub 1 less than or equal to 5. All right? So that's the form. And one thing I want you to notice is that you'll never have any interactions between the features with decision stumps. Remember the interactions between, remember our features lectures we talked about sometimes you need to have the input features interact in some way. Like maybe the product of two features, or if they're Boolean features, you want to say it's not, you can't just add two features if you want it to be and. Like I want it to be, the word ends in ly and it's capitalized. Right? Bitly, maybe. Okay, so if you want to have the intersection of two binary features, you're not going to be able to do that with decision stumps. Because you're just adding, and adding you can convince yourself is more like an or, not an and. So if you want to have conjunctions and interactions between features, if they're not already in existence in your base classifier, you're not going to get them when you boost. Because all boosting does is take linear combinations of things in your base classifiers. Is that clear? It's pretty important to get that. So just to reiterate, you don't get any new interactions between features by boosting. The interactions have to already be there in your base hypothesis space. Typical tree size, our textbook recommends 4 to 8. Yes, please? Okay, which part? The important point that you should realize?
Yes.
Does someone else want to try to paraphrase it? I need to rest my voice a little bit. Okay. Go ahead.
Basically said that if you want like an interaction between two features where you have like a conjunction like and between feature x1 and x2 rather than x1 or x2, you have to like make that before you do the boosting rather than expecting the boosting to do that, because look when you wrote it's like plus f1 plus f2, it's that's like more of an or. You're not going to get a conjunction. There you go.
Yeah. So if I said conjunction, let's make it even easier. And remember when we did height and weight, like big height is, we have to look at the relationship between height and weight to see if it's perhaps abnormal or not. So some kind of interaction would be like your height times your weight. You'll never get an expression of this form if all of your terms are indicators on height less than A and weight less than B. You're never going to be able to get something that's capturing something about the product of H and W. Okay. All right, yes?
Can you give some intuition on why this is better? Like,
Why what?
why gradient boosting works better, because you're actually ignoring any interactions between the features, right?
That's how we're going to use decisions.
Yeah, so this is just decision stumps. This is a depth 1, a tree with only, say,
I'm asking, like, why is this favorable to having interactions between the features?
okay, so let me rephrase it as, is there any situation where you might actually want to use decision stumps as opposed to a deeper tree that can express more interactions?
It's the other way.
Which do you think would be preferable?
The decision tree, because you have
With more leaf nodes?
yeah.
Yeah, okay. Yeah, certainly if your base hypothesis space has trees with 4 to 8 terminal nodes, it's certainly a much more expressive base hypothesis space. And so you can, yes, you can fit more complicated decision functions. That's correct. So why might you not want that?
I know, my question was, why is this method preferable to just creating an individual decision tree separate?
Oh,
because in a decision tree you have interactions between the features, but in this case you simply ignore them.
Okay, so you're saying why would I ever want to do boosting with decision stumps compared to a single decision tree? Okay. Okay. Well, they're different. So with decision trees, you can get some nice interactions, but suppose you have a whole lot of, suppose you have a feature space that's 5,000 dimensional. To touch all those features, you're going to need a huge decision tree. You can't touch more than one feature per decision node. So you're going to have a very large decision tree to even look at all those features. So this may or may not be a good thing. It's not that easy to find the best large decision tree because of our greedy search procedure. Yeah. I mean, other reasons, yes? How does this decision tree have interaction between features? Yes?
In fact, can we use decision tree to design new features for the combination of features which we already have? Because once we train a decision tree, we come to know by using this feature and this feature, we are getting particular features. We can add this feature and train another class.
Yeah, so this was an idea we talked about during the tree lecture. You can do this, yes. You can build your tree and then look at the terminal nodes as basically introducing new features that capture interactions and feed that, for instance, into a linear model. But okay, that wasn't your question. Your question was, how does one get interactions from decision trees? Well, decision trees very naturally code interactions. Okay, I'll let that pass. Go.
So when you're doing boosting, whether it's like a stump or a feature tree, how does that linear combination like add value? Why would you want this? It would almost like the opposite of a decision tree. It's like rather than kind of at each node you're making a decision to get to a certain peak node, it's more like you kind of could go either way. Right? Because you kind of have like different combinations of interactions that you're like allowed to do, I guess.
So
But you want it more between like two functions rather than kind of with a normal decision tree at each node. It's like inherently
an and.
yeah.
Well, I mean, sometimes you want ands and ors. You know, it's, you know, you're good if you're, I mean, you're bad if you're.
It's a different feature. It's like you could either have this feature or this feature.
And either one would be a indicator of a positive label as opposed to a negative label or something.
That's what it's
Okay, so first of all, when we're talking about gradient boosting, the individual base classifiers are now regression functions and not classification functions. So my example here was, they were continuous, not -1 and 1. They were real, the decision stump was giving a particular number, like 2.3 or 0 or something. Although in practice, it's actually, that was probably not a very good example because a decision stump even would actually have two probably non-zero values. So like 2.3 to the left and 1.5 to the right or something would be a more typical, would be a more likely decision stump. So I would picture it, here, can we look at this picture? Here. So here's some data. So the ground truth function is the sync function. The setting. Input space is reals, that's the x-axis. Output space and action space is y's, that's the y-axis. We generated data, these are these circles. All right? This is our training data. And the true thing is the sync function. You can see there's noisy data up here. So let's fit this with a single regression stump. All right? on the top left. That's what happens here. So, okay, in this case it actually is 0 to the left, but it need not be. And here it's 12 to the right. This is the fit of a single decision stump. All right, now let's do 10 of them. Now you can see if you count how many changes there are, there's like 10 of them, because we just added together 10 stumps. So this is why you'd want to add together decision stumps. So you can approximate a function better. This is, I don't know, this 50 and this is 100. We might be starting to overfit here. It's hard to tell. Does this answer your question? Okay. All right. I wanted you guys to see the shape of these linear combinations of decision stumps. So you can see it's like, it still has that piecewise constant nature of a kind of a tree. Okay. All right. So the other thing we talked about was, so what variables do we have, what parameters do we have of gradient boosting that we can tune? There's not a lot. There's, the step size is one of them, right? So what people have found is that you always do better with smaller, you mostly tend to do better with smaller step size. You just have to wait proportionally longer. So here's a picture showing this. So on the left, we're looking at the training error, and on the right, we're looking at the test error. On the x-axis is the number of rounds of boosting we're running, right? So every time we add a new function, we're moving to the right. And the 4 different curves correspond to 4 different step sizes, step multipliers. So lambda equals 1 is like the full gradient step, and 0.05 is a rather slow step. And of course, training error always decreases. But on the right, we have some interesting stuff to look at. So first of all, lambda equals 1, that's this solid line. It doesn't reach the low level of the other guys, all right? So maybe it was taking steps so fast, it passed the optimal space and started overfitting too quickly. What's the best? Well, the other 3 kind of reach basically the same minimum, so that's good. But what you'll notice is that this one, this dashed line, which is 0.5, so it's slower but not as slow as the other ones, it reaches a good minimum rather early, but it overfits pretty quickly after that. So you'd have to catch it right at the right spot. Whereas the other guys stay pretty low longer. So there's a better chance that you'll catch the minimum with your validation step. So that's, rule of thumb is you can set your step size as small as you're willing to wait. Because if you cut your step size in half, you're going to have to take, you expect to take roughly twice as many steps. All right, I was just going to mention a few more variations on boosting that actually get used, on gradient boosting, to give you a sense of the scope of things you can vary on the newest implementations. So there's something that was introduced pretty shortly after gradient boosting called stochastic gradient boosting. And the idea is kind of like stochastic gradient descent, where instead of looking at your full data set to figure out your gradient step, you look at a random subsample. So for whatever reason, in implementations, people tend to use a larger percentage of the data than we use for stochastic gradient. So 50% of the data set size would be typical. It's called the bag fraction, kind of related to bagging. So why would you do this? 2 reasons. One is it's faster. You're looking at half the data if 50% is your bag fraction. So anything you're optimizing on half the data should be roughly twice as fast. Also, it's a tuning parameter for regularization. So you can imagine that if you have a much smaller fraction of data you're looking at in each step, you're less likely to overfit. So in some sense, it's a regularization parameter that you can tune. Now I'm curious, if you can't go a lot smaller than 50%, especially in this case of huge data sets, intuitively, for me, it shouldn't be specified in terms of a percentage. It should be specified in terms of some absolute size of the data that you use relative to how complicated the problem is. So if anyone wanted to experiment with small bag fractions, I'd be interested to see what happens. Okay. The other thing that people do, so the bag fractions is basically like subsampling rows. It's subsampling examples, training examples. So you can also, just like we do in random forest, subsample columns, subsample features. And apparently this is working very well. There's a rather new implementation or version of gradient boosting called XGBoost. It shows up in a lot of top performers on these Kaggle competitions. And it's a version of gradient boosting. I posted the paper. I think you guys should have the background to understand it now. That really is state of the art, it seems, at least in these competitions. And what they report is that practitioners find that subsampling columns is actually really effective, more effective than subsampling the rows, and as far as preventing overfitting. So that could be an interesting parameter to play with. Let's see. All right, any questions on any of these things? Yeah.
When we say subsampling column, that
Yep.
means we are kind of reducing our hypothesis.
Yeah, sure. Reducing your dropping features is reducing the expressivity of your hypothesis space. That's correct. That's right.
Is there anything you like to take
In random forest, you're also subsampling columns, in that case, at every decision node of the tree. So it's related. It's not exactly the same, but yeah. So there's one more concept I'll talk about. It's a little bit beyond the scope of this course, but just for the heck of it. Some of you may have seen, besides gradient descent methods, something called second order methods, like Newton's methods. Then there's quasi-Newton methods. In some sense, they're a lot faster in terms of the number of steps you have to take, especially once you get close to the minimum, or primarily when you're close to the minimum. The issue is that you have to compute a Hessian, which is the second derivative matrix, which is large and hard to compute. It's not hard to compute, it just takes a ton of memory if you want to compute the whole thing. Anyway, so what we can nevertheless think about taking a Newton step instead of a gradient step in this gradient boosting. And in fact, XGBoost seems to do that. So XGBoost is a little bit of a change. It's not quite a gradient, it's more like a Newton step. There's also something called Logit Boost, which you'll find is like the boosting version of logistic regression, but they're doing a Newton step instead. So I'll just give you a rough idea of what this Newton step is. It's pretty easily describable, I think. So we have our objective function j, and suppose we're at a particular point on the objective function. So the way to think about it is picture the quadratic function, a second order function, that's tangent to the objective function at the point where you are. Let me draw a picture. So in one dimension, I don't know. So maybe that's your objective function. It's almost quadratic already. Let me do it a little differently. Now you look, suppose we're in our optimization. So we're optimizing with respect to x. We're changing x. And suppose in our search we're here. This is x sub m. And we need to know where to go next, right? So if this were gradient descent, we would kind of this line and we'd say, oh, the gradient's pointing this way. We want to go the negative gradient direction, so we just take a step in this direction, and then we use some kind of line search to figure out how big a step to take, and we're heading right. Okay. Newton style would be this. At this point, we fit a quadratic. So it would look maybe like this. No, I don't want it to be quite like that. So at this point, it's touching the curve, and the quadratic goes like this. So in a Newton method, you step to the minimizer of the quadratic that's tangent to the curve where you are. So we would step, a full Newton step would take us right to here, the minimum. So what does that really mean? It means we would jump to here for the m plus first. All right. Now, this is just one dimension, so there's only two directions to go in one dimension, left or right. So this is not so interesting. But if we're optimizing in this space in 2 dimensions, we might have, for instance, the gradient is this direction, but the minimizer of the quadratic function at the point tangent to me may be in that direction. So the gradient direction may be this way, but the direction called the Newton step direction towards the minimizer of the tangent quadratic is a little bit different. It's over there. So that's the direction that you'd go in a Newton step. So we can apply this, and people do apply this to gradient boosting. And it turns out it's not difficult to do a Newton step in this setting because all the off-diagonal terms of the Hessian are 0, it turns out, because of the form of the objective. Why is that? Here. Suppose we're going to take another derivative with respect to, so we took the first derivative with respect to f of xi. The second derivative for the Hessian would now take a derivative with respect to f of xj. So if j is not equal to I, so first derivative only left terms with x sub I. Now you take a derivative with respect to xj, there's no terms left. The second derivative will be 0. So we only have second derivative terms if we're taking derivative with respect to the same thing twice in a row. So this is why second order methods are plausible with this objective function. Okay. So that's all I wanted to say about Newton method. Yeah?
Why is the xg boost taking the column? Why is that approximately quadratic?
The column, what?
You said the xg boost.
Two entirely different things. XG boost, in their paper, they proudly say that they were the first to apply column subselection to gradient boosting method, and that it works really well. Besides that, another difference is that they use this Newton step direction. And besides that, another huge set of things that they did is all related to computation and doing things very efficiently. And they're very clever about how they build their trees. XGBoost is a gradient boosting system based on regression trees, I should also say, for any loss function. I think it's extreme gradient boosting. It works for really large data. It's parallelized nicely. It's smartly implemented. All right. Cool. So all right, Peter, any graders here who can help me pass this stuff out, the exams out? Or not?